Hey everyone, today I'll be talking about our work on creating high performance durable data structures with minimal ordering. This is work done with my advisors Mark Hill and Mike Swift at the University of Wisconsin. Let me start off with a brief overview of this talk. Newly available persistent memory such as Intel Optane enables applications with durable in-memory data that can recover after a system crash. We analyzed some of these recoverable applications on Intel Optane and found that 73% of their execution time was just overhead, mainly spent in flushing data out to persistent memory. We looked into these flushing overheads and found that their costs could be minimized significantly by overlapping multiple flushes to persistent memory. Accordingly, we created mod or minimally ordered durable data structures, a library of recoverable data structures such as map, set, stack, vector, and queue. Mod data structures leverage optimizations found in functional data structures to increase the overlap in flushes and offer speedups of 40% on average compared to software transactional memory. We've released our code and it can be found at the link on the slide. Here's the outline for this talk. I will first set the context for the work that we have done and discuss the performance bottlenecks of persistent memory applications on real hardware. Based on these observations, I will describe the design of our high-performance mod data structures and finally end with a brief evaluation. With the release of Intel Optane memory last summer, I can finally say that persistent memory is here. Persistent memory is just a term for non-volatile memory that is on the memory bus, and this can be directly accessed from user space via regular load and store instructions. Such access enables applications that store their in-memory data durably in persistent memory and thus can recover their progress after a system crash or a power failure. The introduction of persistent memory into our system divides the available memory into volatile and persistent domains. An application's data is not durable when it is in volatile structures like the caches or CPU registers. Hence, programmers who want to build recoverable applications must explicitly flush data out to the persistent domain for durability. Moreover, this data movement must be atomic with respect to failure. Otherwise, partial updates like the one on the slide right now may corrupt even durable data structures. A common approach is to use software transactional memory or STM to provide failure atomicity and durability for programmers. I will illustrate the role of STM with a simple example. So here we have an array of elements in persistent memory. We want to swap two elements x and y in this array. Now, before we can overwrite the value of x in this array, the STM library kicks in and saves the old value of x in a log. It makes sure that this log is durable before we overwrite the index. With one flush instruction, we can launch the flush operation. To make sure that the log actually reaches persistent memory, we add a fence that stalls the CPU till all outstanding flushes are complete. At this point, the data can be safely overwritten and flushed out to persistent memory. We would have to repeat the same process for overwriting the value of y with x. Now, if there is a crash at this moment, any data that is in our volatile caches will be lost. Our durable data is now inconsistent because we have the value y repeated twice. Fortunately, we can use the lock to restore the array to the last known consistent state. So, while STM is convenient for programmers, we found that this approach is inefficient on real hardware, as we see in this next graph. Let me describe this graph first. Here on the x-axis we have our workloads. The first group of workloads involves random read-write traffic to different durable data structures. The second group consists of full applications such as a breadth-first search that uses a durable queue and vacation and memcached that use durable maps. On the y-axis we have execution time, which is normalized so that the total execution time of each workload would sum up to 1. So right off the bat, we notice two things. The first is that the execution time actually spent in useful work is a very small fraction, and it's shown in green here. In fact, 73% of the execution time is just overheads, which mostly come from flushing data to persistent memory, shown in orange here. These flushing overheads also include the cost of using fences to make sure that the outstanding flush is complete and that the data has become durable. There are also some other logging overheads, but these are quite small in comparison. So, to improve performance, it's clear from this graph that we must focus on reducing these flushing overheads. To zero in on the flushing overheads, we created a micro benchmark that interleaves flushes and fences as shown here. Let me actually zoom in so that you can see it a bit better. Now, the total runtime of this micro benchmark will be plotted on the y-axis of this graph. We now eliminate every alternate fence from this micro benchmark. This means that we will launch two flushes to persistent memory, one right after the other. The following fence has to wait for both of these flushes to complete. By thus overlapping two flushes per fence, we can actually reduce the total flushing time roughly by a factor of 2, even though the number of flushes to persistent memory has not changed. As we remove more fences from this micro benchmark, the execution time keeps falling, but with diminishing returns. We found that this reduction in flush overhead as these flushes are overlapped actually follows Amdahl's law, and our paper contains a useful analytical model for this. Now, fences are easy to eliminate since this is a micro benchmark, but how do we actually do this in a real application? For context, in our STM workloads, we found that transactions can have up to 23 flushes and 11 fences. Let's see if we can do better with our mod data structures. So, based on our analysis so far, we've concluded that we need to minimize ordering constraints to improve performance. There's actually a useful technique called shadow paging used in file systems and databases to reduce ordering overheads. The key idea is that overwriting data results in greater ordering, and so when data is overwritten, log writes must be created and ordered before data updates. For minimal ordering instead, shadow paging performs out-of-place data updates. Let me illustrate how shadow paging works by reusing our old example of swapping two elements in an array. This time, we do not require any logging. Instead, we first create a copy of the data structure or a shadow. We go ahead and perform the two updates directly in the shadow without modifying our original array. Finally, we flush this new array and use one fence to ensure that it becomes durable. And subsequently, the application begins to use the shadow array instead of the original. If there was a crash at any intermediate point in the application could still use the original unmodified array, which remains in a consistent state. Taking a step back, we have now actually reduced ordering overheads, but introduced some copying overheads and are flushing a lot more data. If only there was a way to perform out-of-place writes without copying so much data. Well, it turns out that functional data structures have already solved this problem. You see, in functional programming languages, most data structures are immutable, which means that they cannot be modified once they are initialized. So, when a functional data structure gets updated, like this array here, the original data structure is not modified, but a new and updated copy of this data structure is created. However, there is a trick here. The trick is that these data structures, even arrays, are implemented as trees. The updated copy reuses most of the internal nodes of the tree. In our experiments, we see that the new data is less than 1/100th of 1% of the size of the original data structure. This class of optimizations is called structural sharing and have been developed for most common data structures, and their implementations can be found in many languages including C++ and Java. So, to create our minimally ordered durable data structures, we could have actually done the hard work and implemented them from scratch. Instead, we did the smart thing and created them on top of existing implementations of functional data structures. So, we used a persistent memory allocator to allocate the data structure's internal state in persistent memory. We modified the data structure implementations to flush out all updated cache lines to persistent memory. So by doing these steps, we've made the data structure durable. Making it failure atomic is easier as we can combine the existing out of place updates and add some fences, which we'll discuss in a couple of slides. This approach allows us to actually benefit from over 20 years of research and development in functional data structures. Our mod data structures support high-level read and write APIs similar to the C++ standard template library. Most importantly, this abstraction hides the grimy details of persistent memory programming, such as flushes and fences. For common use cases, we can also hide the fact that there are out-of-place updates happening. Let's try to use these data structures to see how they work. The programmer accesses our mod data structures through a pointer, and the data structure itself is a black box that hides a functional implementation. We provide update methods with the guarantee that the data structure is updated atomically, consistently, and durably with one fence when the function completes. If there is a crash during the execution of this function, the original version of the data structure is preserved. Under the hood, what actually happens is that the data structure gets updated out of place. Flushes to any dirty cache lines are overlapped, and there is a single fence at the end of this update function. If the update completes successfully, the pointer is swung to point to the shadow instead. And once the new shadow is flushed and durable, we can go ahead and reclaim the memory of the old version. Now, mod data structures can also be used for some advanced use cases. We discussed the case with multiple atomic updates to a single data structure in our paper. In this talk, I will briefly cover the case with multiple updates to different data structures. So in this case, we do have to expose the fact that there are out-of-place updates to the programmers. The programmer updates the relevant data structures and gets back the respective shadows of each of the updated versions. Then they use a simple commit API that atomically replaces all of the original data structures with their updated shadows. Where are the flushes here? Well, the flushes are still hidden within these update functions and overlapped with respect to each other. The commit implementation has one fence to ensure that all of the updated shadows have become durable. At this point, there is a short transaction to atomically swing all of the pointers to point to the shadow data structures. And in fact, in our paper, we describe an alternate method that does not even require transactions for updating multiple data structures atomically and is sufficient for many use cases as we've found. Now, let's move on to the evaluation of mod data structures. We built our mod library using an existing library of functional data structures as well as an existing memory allocator. For our baseline, we compared against the software transactional memory implementation in Intel Persistent Memory Development Kit, which uses hybrid undo-redo logging. And our source code is released and can be found at the link here. Now, this graph shows the performance, the execution time on the y-axis and the workloads on the x-axis. And it's in fact the same graph as earlier when I was showing the performance overheads of STM workloads. I will present the performance of our mod data structures in three parts. We observe that mod data structures are able to improve the performance of data structures that are traditionally pointer based by 43%. Such implementations involve map, set, queue, and stack. Mod data structures are improved performance by reducing flushing overheads and eliminating logging overheads completely. For vectors, mod uses a tree-based data structure as opposed to a contiguous array in the baseline, and so require more flushes to make durable and failure atomic. Vectors are an area of future work, maybe by you. And then moving on to our full applications, which is where we really feel mod shines. We have breadth first search that uses a queue, vacation and memcached that use maps. Mod is once again able to improve performance by 38% by eliminating logging overheads and significantly reducing flushing overheads. So, to summarize, persistent memory with the introduction of Intel Optane has enabled recoverable applications. Our analysis on of recoverable applications on Intel Optane memory revealed that a majority of their runtime is spent in overheads, which mostly involve flushing data to persistent memory. We created minimally ordered and durable data structures that leverage optimizations from functional programming to increase the overlap in flushes and improve performance by 40% on average compared to persistent memory development kit. If you have stayed till the end of this talk, you probably have some questions. You can ask them on the Slack channel or send me an email. Thank you.